Please find a seat. We will begin next section. Hello, everyone. My name is Pedro Tang. Currently, I am in Max Planck Institute. I was Shoucheng's postdoctor from 2015 to 2017. It is my great honor to chair this section. Okay. In this section, we have two speakers. The first one is Professor Ronghui Gu. He comes from Columbia University.
Hello? Okay, cool. So welcome back, everyone. So I'm Ronghui Gu. I'm now a computer science professor from Columbia University. And today I will not talk about physics. Instead, I will talk about some topics that Shoucheng has strong interest in the field of computer science. That is towards building trustworthy systems software. So we all know that system software runs everywhere and have a big impact to our our daily life. And we have to totally trust them, but they are not fully trustworthy due to program errors. Right? A single program error in the system might give you a blue screen and fail a presentation, right? Which might not be a big deal, but in some cases, a single program error in the system software may lead to a disaster. So take this Toyota's killer firmware as an example. So in 2013, this unintended acceleration of this Toyota car killed one of its passengers. And this accident was caused by a single Stack Overflow bug in the assembly module, which only contains 350 lines of code in total. And so how can we avoid such kind of program errors? And how can we avoid such kind of accidents? So can we rely on more tests? So the answer is probably no. As Dijkstra says that program testing can be used to show the presence of bugs, but never to show their absence. Right? So I will use this example to show why tests will fail in this scenario. So suppose we want to implement some program to calculate the square of x plus 1. So this x plus square of x plus 1, we call it specification. You can view it as also the designer's intention of this program. But the hardware does not provide the operator to directly calculate the square. So we have to implement the specification in some programming languages. Like we can do it like this. We calculate the square of x plus 1 by x plus x times x plus x plus y. Don't ask me why I implemented it like this, right? So, and then we can use testing, right, to test whether this program is correct or not. So we simply design some test cases and run the program to see if the results are the same with the expected ones. Like we try this program with x is equal to 0, and we find out both sides are equal to 1, so it passes this test case. And for x equal to 1, we run it again and find out, well, it also passes these test cases. So after it passes all the test cases, we say, well, yes, this program has been tested. But the thing is, if we made a mistake, and the program is written like x plus x plus x plus 1, it can still passes all the test cases. But we all know that apparently this program has a bug, right? So that's why program testing does not work. So what else can we do? So now many people, including me, will stand out and claim that the formal verification is a cure. So we believe that formal verification is the only knowing way to guarantee that a program is free of program errors. So by formal verification, we mean to use mathematical ways to prove that the program indeed satisfies the specification under all possible inputs and under all possible executions. So for example, in the previous program case, right? So we can prove that the computation model, the program, indeed the same with the computation model of the specification by applying this sequence of math rules, right? We can apply first the associative law of plus, and then do the factorizing, and then we apply the commutative law of plus, and then do another factorizing, and then by definition, we show that, well, the right-hand side is indeed the square of x plus 1, right? Looks so great, but why there are still so many bugs? Why we can't simply apply these techniques, right, to secure all the systems world, right? The reason is, first, it's very difficult, and second, in some cases, it's even impossible. So let's consider this special case that if the specification is simply that the program will always terminate. So this is a question asked by Shoucheng during my visit here at Stanford on March the 13th, 2018. So this question asked by Shoucheng is a very good question because this reduces the formal verification problem to the very famous halting problem, right? So the halting problem is a problem of deciding whether a given program will ever halt or not, right? We all know the answer, right? So in 1936, Turing proved that general algorithm to solve the halting problem for all possible programs can't exist. Right? I just realized that Shoucheng learned this halting problem from Zhang Yang during his PhD study at Stony Brook, right? From the video showing on the Thursday night. Right? And so after our conversation in his office, we took the picture, right? The picture I showed previously. And he also said that, well, he has a dinner appointment and asked if I would love to walk him to the restaurant. I said, yes, of course, right? So let's walk to the restaurant. And during our walk, we go through Turing's proof of this halting problem. So now let's do it again together. How Turing proved the halting problem. So suppose we have a general algorithm that can decide whether any given program can terminate or not. So suppose we have such a general algorithm. So we can implement a function called v. This v stands for verification. And if the given program terminates, this function v returns false. And otherwise, this function v returns true. So suppose we have such a magical v, function v. And then we can construct a paradox function, which takes program p as an argument, and it will calculate this something called VPP. So what's the meaning of VPP? So we know that program can take inputs, right? And all the program can also be represented as binaries, as 0s and 1s. So this PP means the program P takes the binary representation of itself as an argument. So the program P takes an input, and this input is simply the binary representation of this function P. So that's the meaning of PP. So we send this program to this magical V. So if it gives us a true, we go to infinite loops. And if it gives us false, we simply go to another branch and return true. So this is a paradox function we construct using this magical V. And then let's consider a special case, this paradox. Well, I can see many levels of wrappers. And so paradox. So if this program, paradox, loops forever, it means that by the definition of function v, we know that since this paradox as arguments loops forever, so it should belong to this branch and return true, right? And since it loops forever, then it's return true. And then if it's, it should be kind of like, it should be true and false. I'm sorry, it's a typo. Yeah. So it should return false, and yeah, and then it should jump to this branch and return true. So by the definition of this paradox function, we know that this paradox terminates and a contradiction. Sorry, this is a typo. It should return true. This should return false. Sorry. And if the paradox house, right? And then by the definition V, it should go to this branch. Well, it's typo, so it should return true. So in the definition of paradox function, it should go to the first branch and go to the infinite loop. So paradox indeed loops forever. So another contradiction. You can see that, well, this is a proof done by Turing showing that, well, such kind of algorithm can't exist, right? But this proof is not a constructive proof, although it's a very beautiful one, right? Turing didn't find an counterexample, right? A program that we can't decide whether it can terminate or not, right? And so Shoucheng asked me another question. Is there a simple and a specific program that we can't decide whether it will ever halt or not? So he asked me the question during my talk on August the 2nd, 2018. That is on the Danhua's professor workshop. And that is also the last time I met with Shoucheng. And he asked me this question. I said, well, I'm sorry, I don't know the answer, but I can get a pretty close answer or an example that close to that answer. That is this program. This is a very simple program that was written in less than 10 lines. And what it does is simply that it takes a positive integer I as an input. So if I is even, we divide it by 2, means that it's decrease, right? So if I is odd, we triple it and add 1 to it. So it means that it will increase. So we're repeating these operations until I is equal to 1. So let's run this very simple function with some examples. Suppose I is 5. And so then 5 is odd, so we triple it, and plus 1, we get 16. 16 even, we divide it by 2, we get 8. We keep going until we get 5. So it terminates very quickly. And let's try another integer like 13. And 13 is odd, we triple it, add 1, we get 40. And then we divide it by 2, we get 20, keep going, then we get 5. And then we can repeat the sequence of 5, so it also terminates very fast. So can we conclude that this function always terminates? Yeah, the answer is probably no again, because you can see it's a conjecture, right? It's class conjecture, also called the 3n plus 1 conjecture. Even for this very simple program, we don't know whether it will always terminate or not, and we can't do the proof. And during the workshop, I believe Shoucheng and Xiaoliang and I, we discussed lots of ideas to do the proof, but apparently we made no progress along this line.
It's just not known whether it will terminate, or is it undecidable?
So first we try all these integers, and it always terminates. But we can't prove that it terminates. We guess that it will always terminate, but we can't do the proof. So this figure shows how many steps it takes to terminate for all the integers less than 10,000. You can see that, well, so it always terminates pretty fast. And the biggest number of steps to terminate is 261, taken by I is equal to 6171. And from this figure, it seems that, well, there are some laws there, right? There are some rules, but we just can't do the proof. Yeah. So you can see that, well, how despairing, well, the researchers in our field is, right? So we are very despaired because let's suppose this gray circle is the programs that we have built that runs everywhere, and the programs that we can verify, they just belong to this very small red circle. Very small one, right? But in the past few decades, so the researchers in my field, we work very hard and try to grow this right circle, try to grow the domain that we can verify. So in 1998, French researchers verified the control systems of Paris Metro Line 14. And in 2005, European researchers verified the flight control systems of Airbus A380. And in 2005, sorry. Oh, okay. Okay, it's a joke. Okay. Yeah, we haven't done for Boeing. Sorry. Yeah. Yeah. And in 2005, Xavier Leroy from India built ComCert, the first verified C compiler. And in 2009, Australian researchers built SL4, which is the first verified sequential OS kernels. But the thing is, you can see that all these systems are sequential systems. So what about concurrent systems? So you know that concurrent systems, the different threads, different CPUs, they can interleave in arbitrary way, so makes the verification, makes the proof much harder. So in a very long time, many researchers think it's almost impossible to verify a concurrent complex systems. And even it can be done, the costs will be far exceed the sequential ones. But in 2015, my colleagues and I, we built Certicos, the world's first fully verified concurrent OS kernel. And you can see that both Certicos and ComCert are proved using the tool COQ. So COQ is a proof assistant and won the ACM Software System Award in 2016, and is famous by some great results proved using COQ, including the 4-color theorem, including the ComCert compiler, and our Certicos. And then how we do the proof, right? So we identify that the bottleneck to do the concurrent reasoning is not the proof technique. Instead, the bottleneck is how to write specification. So we introduce a new notion called deep specification, and can be represented by this single formula. So Shoucheng asked me, what is a single formula to stand for your work? I think, well, it might be this one, right? So the meaning of this formula is so this represents the deep specification. So we call L2 a deep specification if this over interface captures all we need to know about running the code M over some under interface L1. So once you do the proof of this deep specification, so any property about the M over L1 can be proved using the over interface L2 alone, and there's no need to look at the code M anymore. And then how we prove that the specification captures all we know about the program, we do it by simulation. Yeah, so R is a simulation between two states. I will explain here. So this can be done by simulation, showing by this diagram. That's starting from two states that are related by this R. You can view that, well, these two states are not distinguishable by some observation R. So that's the definition of R. So start from these two indistinguishable states. If the specification takes one step and the code, the implementation, takes multiple steps, and then we have to show that the resulting states also are indistinguishable from this observation R. You can see that we borrow ideas from physics, right? So if we can't observe something, we claim that it does not exist, right? If we can't observe any difference of two things, we claim that they are the same. And so using these deep specifications, we can achieve the modular verification or modular proofs. So suppose we have two deep spec and they share the same underlying interface, we can compose them horizontally like this. And if two of them share the same adjacent interface, we can compose them vertically like this. And these deep specifications can also be composed in parallel in the concurrent setting. So we use this approach and build 33 layers to verify Certicos. And this Certicos was deployed on this Landshark machine by DARPA, which is a military robotics. Right? So you can see that, well, so that's how we grow this circle, right, to cover some part of the concurrent system. And then the next question is, how about the blockchain systems? We all know that Shoucheng is a big fan of blockchain, right? So do we need to verify the blockchain systems? And how can we verify blockchain systems? So first, let's talk about what is blockchain. So Brian has briefly described what blockchain is, right? So we all know that blockchain is very popular in the past 2 years, and its market cap has been increased from $14 billion to $300 billion in 2007. And the number of smart contracts, which are the applications running on top of blockchains, have been increased from 100,000 to 1 million, also in that single year in 2007. And so the reason why so many people are crazy about blockchain is because in this system, there's no need to trust a single centralized authority. And instead, we trust in math. Right? In this system, you can view blockchain as a world computer that no one can stop. So we don't rely on any single authority to make decisions. Instead, all the nodes working in this networks, they follow the same protocol or consensus algorithm to reach consensus, to make decisions, to maintain the system, and move forward. So there's no single one that can change the historical data in this blockchain, and everyone has to follow the same rule as long as there's no 51% attack. And so the protocol on the math side is well designed and beautiful, but however, the code that implements this protocol has bugs and is vulnerable. So we can see that many attacks have happened in this field and utilize these bugs to steal tokens. So it leads to more than billions of dollars of financial loss in past 1 year. Right? So then we start a company called Certic, and to apply our verification techniques in this domain. So this company is also invested by Shoucheng and Danhua VC. So they're actually our first investor. And I will skip this part. So we apply our techniques to verify smart contract and blockchain systems. And this is a demo of how we can detect bugs in the system. I will skip them. And so we have already served more than 170 clients, and we have verified more than 100,000 lines of code, and we have secured more than $4 billion of cryptocurrencies. You can see without Shoucheng's help, we can't achieve this. So without Shoucheng's help, this world of blockchain will be much more vulnerable. And here, this is another example of quantum programs. Can we verify quantum programs? This is an ongoing work, and I will skip it. So this is a program of the GHZ gate. And we know that the computational complexity of this program grows exponentially with n, which is the number of qubits. But we can do the proof by induction in these two steps. And this proves, the complexity of this proof will not grow with the increase of n. Right? So you can see that, well, we work really hard trying to grow this right circle, but we know that we can't cover the entire gray circle, not only due to the halting problem proved by Allen, but more fundamentally due to the Gödel's incompleteness theorem. Gödel proved that in 1931, Gödel proved that no consistent system is capable of proving all truths about the arithmetic of the natural numbers. It means that even if some natural number related statements are correct, we may not be able to prove it using consistent math systems. And so Einstein said that he went to his office at the Institute for Advanced Study just to have the privilege of walking home with Gödel. You can see that Einstein shows strong interest in Gödel's work, although it's not in physics. So I would say that I believe the reason why Shoucheng and Einstein and many of us have strong interest in the fields beyond the field of our own study, of our expertise, is because of the curiosity to this unknowing world, even though we know we can't discover all of it. Right? So this curiosity leads us here, and I believe this curiosity also leads Shoucheng to what he has achieved. That's all. Thank you.
Any question and comment?
So in the quantum case, I'm not sure what is it. Like, are you trying to prove one set of gates achieves the same as another set of gates? Like,
yeah, so for these quantum programs, I don't have time to explain, but I can explain now. So we have a GHZ circuits, right? So it takes n qubits as input. Suppose that they are all starting with 0 state. And so on this side, there's a program that we use to implement these circuits at a high level. And those red lines are the specifications we write for this program. So we want to prove that for any n, this program always give you the resulting qubits always satisfy this state, always in this state. So we want to prove that this program is correct, that it always give you this state. And this can be proved by induction that when n is equal to 1, this circuit is simply an H gate and give you the desired state. And if when suppose that for any number of qubits are less than equal to I, it give you the implementation satisfies the specification. We can prove that by applying the C0 gate to the previous qubit and the new qubit that starting with a 0 state, it will also give you a state that satisfies the specification. So it can be proved by induction like this.
But that seems very special. It seems like if I don't have such a simple output, which will be the case where you really need the verification.
So the thing is, we know that, well, kind of like most of these quantum programs or algorithms, the computational complexity increases, grows exponentially with the increase of number of qubits. But many of them, they might kind of have this repeat pattern, and you can't compute the program on the classical computer, but you can prove the correctness of such of these kind of programs in a simple way. So again, we can't cover all possible quantum programs. Majority of them, I believe, definitely belong to the gray circle. But we're just trying to grow this red circle to prove as many as possible. Go ahead.
Actually, more than 1 month ago, I was in another conference. I talked to Intel computer scientists working on AI in a data center. I used to work for Intel, actually make CPU. You know, the things we hate, and the PC and the cell phone is the virus infection, right? So that if we can apply the blockchain principle, you know, for every PC or the cell phone, we embedded a chip or into the CPU, you know, can prevent all those kind of infections of the virus. Is it possible? Can say that about, you know, you have hundreds of millions of cell phones and PCs. I mean, you really cannot, as you said, cannot check out all those parts.
Yeah, well, so the thing is, although I don't understand your idea of applying blockchain in the hardware design, but the thing is, first of all, in hardware design, so this formal verification techniques has already been widely deployed because hardware, in most cases, is much simpler than software. So, but for software, so whatever hardware you design, you still rely on programmers to write programs on top of it. And especially for some safety critical systems, we still want the guarantee of the correctness of these softwares built by developers. So I don't think there's some easy solution to kind of like solve all these cases. But as I said, we have to kind of like try to grow our verification techniques, try to grow that right circle. Yeah, I still don't believe there's a simple solution. Right?
Okay. Sorry, about the proof, you're looking at a black box program and only know what output it produces, right? Is that what you're trying to prove?
The kind of like this, the techniques I described here, they relies on the access to the source program. But the thing is, how to define the correctness of the program? We use this black box thing that we only observe the pre and post conditions and making sure that, well, these steps of programs that give you the equivalent behavior of that black box. Right.
Okay.
Okay, we still have time. Any question? No, let's.
I have a question. So, apart from the the hacking for the blockchain system, there are known many forks for the blockchain systems. So can you comment on that? Is that solvable, or is more like a social thing? And if that's whatever your comments are, what about it in your system? like the forking is
Okay.
not possible.
Yeah. So the thing is, so blockchain system, as I said, so everyone have to follow the same rules, right? You have to reach the consensus. But the thing is, let's say if you can't reach the consensus, let's say if there are two parties of the community, then it will lead to a fork of the blockchain, right? The thing is, well, then we will say that, well, we always want to pick the longest the chain. If let's say the community forks, right, we always want to pick the longest chain. So there are many kind of like design this algorithms trying to avoid such kind of we call soft forks and so on. So this is more like trying to prove the robustness of your algorithm. We can do the proof similarly here, but the target will not be the code, will be the protocol. But there's another kind of forks called hard forks. Yeah, it means that because here, let's say in this the DAO attack, so there's a single bug that enables the double span attack. So it losses actually more than 15 million loss. And then the community of this blockchain, they got divided into two communities. One community said, well, we have to trust in blockchain, so we design the protocol like this. Even if the hackers utilize the bugs in our protocol to steal tokens, we still admit, well, our tokens were lost. And there's another community said, well, we don't admit the loss, so let's revert back. Let's try to change the historical data. So you can see this does not follow the design of blockchain, but the community just divided into two. So this is what we call the hard fork. So hard fork is something can't be solved at the software level, I would say. Yeah.
Okay, so thank you.
Okay, thank you. Thank you.
The next speaker is Stanley Qi from Stanford University.